Hello, welcome back to your Theory 1. Okay, so we will now discuss your Module 3, which is the analysis of statically determinate trusses. So, previously on the Module 2, we discussed about the fundamentals of the analysis of statically determinate structures. But for this module, we will be focusing on the one type of the structure, which is the trusses. So, analysis of statically determinate trusses. So, this is your Module 3. So, in this video, we will be discussing in Unit 1 the method of joints. Okay, we call the method of joints way of analyzing your determinate truss. Okay, so this is your Unit 1. So for this unit, we are going to solve member forces, or if it is needed, then we will be solving what we call as the stresses. So of course, you know how to solve stresses based on, of course, that is discussed in your mechanics. So if you have a force acting on an area, all you need to do is distribute the force within the area, and that is what we call a stress. Okay, so we will be solving member forces or member stresses of determinate trusses by using your method of joints. Okay, so this is important for trusses. Okay, so these are the assumptions which are to be used in trusses, in analysis of trusses, and of course this is true in all methods, okay, of the analysis. So trusses are analyzed as joint loaded structures. So actually I discussed this one in the introduction. Okay, what are the different types of commonly used different types of structural forms. Okay, so I discussed there the difference of trusses, beams, and frames. Okay, and the similarities, of course. So trusses is only assumed to be loaded within the joints. Okay, in the case that loads are within the members, these are to be distributed with the member joints for the purpose of analysis. Okay, so since of course if we will try to consider the actual scenario, of course if let's say that is a roof truss. Okay, so the truss or the roof itself is receiving a pressure, a wind pressure. So actually what is in contact with the wind pressure, or what is being loaded by the wind pressure, is the area or the entire roof. So what do you expect if we are going to apply this one on the truss? That is of course loaded on the member itself. But of course, since the analysis of truss is only assumed to be loaded at the joints, then we will transfer whatever load within the member, we will transfer that one in the joints. Okay, so that's it. And another assumption here is that all joints are connected by hinges, okay, in plane trusses. So if we are referring to 2D trusses here, okay, the connections are all hinges. Okay, so that is discussed, of course, also in your introduction. And then if we are talking here of space trusses, that is now a ball and socket joints. So what is the difference of hinges? Because in hinges, that is just of course referring to free movement or free rotation within the plane. But if it is a free rotation within the within a 360 degrees rotation, or that is a 3D rotation, free within the 3D rotation, then that is what we call as the ball and socket. Okay, so actually just hinge is just a simplification of ball and socket from 3D to 2D planes or 2D trusses. And third there is that all members are under pure tension, or that is under pure compression. Since again, as I explained on the introduction of these trusses and beams and frames, that trusses, all the members of trusses are purely under compression or tension, because there are no member moments. Okay, there are no member moments, only compression or only axial loads. So it's either tension or compression. So if we will try to consider this as the member AB of a truss, okay, if that is a member of a truss, then whatever, okay, so whatever is experienced on this other end of the member is the same all throughout within the member. If that is the compressive force FAB, then that will be the same here as the compression force FAB. By the way, you need to recall the sign conventions of tension and compression. If we say tension, that is the arrow is going away, the figure. However, in this case, that arrow is going towards, so that means that is compression. Okay, towards, because of course it is going towards the receiving area, so it means that it's being compressed. But if that is going away, then that is stretching the body, so that is tension. So that is of course the same. If this is a tension or compression, it doesn't matter, as long as what I'm trying to say here is that the entire member is experiencing a single stress or a single force. Tension, if that is purely tension, then all will be the same magnitude, and then if that is compression, then the same thing. So if let's say we have a sign convention, of course, to follow for the sake of discussion, for the uniformity of the discussion. So if we are considering the force at the other end, let's say this is member AB, then considering the force within the joint A of your member AB, let's call that one as the force from A to B, from joint A of your member AB. So that is how this is read. And that one is force at joint B of your member AB still, since of course A and B are the end points, or that is the end of the member. So again, AB, force AB, it means that is at joint A. Force BA, that is at joint B, but still they are within the member AB. So again, entire will be the same. So FAB is equal to FBA, even if that is reversible. FBA is equal to FAB. So please do not forget about this. So that is what we will be using for the analysis of trusses. Using different methods, of course. But for now, we will now focus on what we call as the method of joints, since that is our focus of discussion here in Unit 1 of your Module 2. So what we are going to do is to have an example here. So let's have this as an example. So determine the member forces of the truss shown in the figure. So actually, this is our example on the discussion in your Module 1 regarding reactions. Actually, we solved the reaction of this from the Module 1. But of course, the solution is still here. We can review that one. And this is the original figure, and then we substituted the answers, and this is now the final, with the answers of the reaction. So, we will try to focus on top. As I've said before, in solving reaction, all we need to do is assume a direction, since of course we do not know yet the correct direction. But as what I'm applying before, as what I did on the Module 1, I suggest, so that you will not be confused, always assume a positive direction. Wherein we agreed on the previous discussion that positive will be going to the right, going up, and if that is a moment, clockwise. So going to the right are the positive directions. So that is my initial assumption, and going up. This is a hinge of two reactions and a single, since that is ruler. So if we want to solve this one, since of course we cannot solve the member stresses or the member forces without solving first the reaction. So let's start by summating the forces vertical, which is going up positive. So all the forces going up is positive, that's only EV, and of course the rest which are vertical, these are the going down, all of these. So 3 times 30 and then minus 15, so these are negative since that is going down. And then simple algebra, you will have now your EV to be 105 kips, that is positive, so it means our assumed direction is correct, so upward. Let's take a moment at E. If I will take a moment there, EV and EH will be cancelled, so we are only solving A sub H. So take a moment clockwise, I will assume that to be positive, so all of this will be clockwise. So actually I can factor out the force itself 30. All we need to do is summate the moment arm, which is 16, 32, and then 48. So that is this one, positive moments. And then 15, which is still clockwise. So 15 times the moment arm, 64. By the way, that is 4 by 16. So 16 each of these distances. And then lastly, AH with the moment arm of 12, but that is counterclockwise, so negative. This is a simple algebra. Transpose, divide both sides by 12. We will have AA sub H to be 320 kips. Positive, so it means our initial assumption for AH is correct, going to the right. Now finally, if you want, you can take a moment at any other points, but I'd rather use the summation of force horizontal, since that is simpler. If I will summate forces horizontal, these are the only two forces horizontal. So AH is going to the right, so positive. However, that is already 320. E sub H, which is positive, since that is going to the right. Therefore, transposing this one and negative 320, the negative only means that our initial assumption is wrong. The direction is wrong. So all we need to do is reverse the direction. So my initial is going to the right. So that means I will reverse that one that is supposed to be going to the left. Okay. So now we have the reactions here. So again, we cannot solve the member forces without solving first the reactions. That is of course the general procedure, unless there are some cases wherein we can start solving the member forces at a given points and then going towards the reaction, but seldom that we can apply that one on most of the structures. Okay, there are only special cases like that. So the main or the general procedure is to solve first the reaction and then transpose the reaction and the loads to your member forces, or to your member, to have your member forces. So let's try now to continue. We have already now the reactions. Okay, so I already included it in our figure. So that's why we call this one method of joints, because it is literal. We are going to consider each of the joint to analyze the truss. So we call this one method of joints. Okay, so first of course we need this one, because later on we will represent the members as forces, or if you say forces, that is an arrow with direction. So for us to represent, let's say for example AB, member AB, for us to represent that one, since we will try to consider isolate each point, and that is what we are going to analyze. So for example, I want to isolate joint C. So I will isolate that one, and the three members connected, I will represent these ones with arrows. So if let's say I assume that this member is compression, the arrow will be going towards joint C. So isn't it, that is again what I've said. Our assumption is that tension is going away the body, and then compression is going towards the body. So an arrow going towards a point means compression, an arrow going away a point is a tension. Okay, so that is what we are going to do. So in my solution, let's start with A and then moving towards your point I. Okay, so we are going to call this one, separate joint by joint and analyze this one, and then whatever members connected to the joint, that will be the forces which we will be solving within the joint. So that's why we have what we call as this member of joints. Okay, so analyzing joint by joint, so up to the time that we will solve all the members connected in all the joints, then that means we solved or we computed all the member forces. So let's start with the joint A. So let's isolate joint A. Okay, at joint A, that is your point A, we have there two connected members, but at the same time that is where the reaction is located, or the support is located. So there should be the reaction applied within the point. Okay, within the point A or joint A. So if I will try to isolate that one, that is a reaction going, okay, going towards, so it means it is compression. So what else? By the way, let's try to stick to the assumption of assuming a positive. Okay, I mean assuming a tension always. So it means in my solution, as if we will try to continue, if the member force is still unknown, let's assume that one to be going outwards, or it means assume that one to be tension. But actually, if you are now doing this one in your own, you can actually assume that one in any direction you want. Especially if you are already used in solving this, you can assume by your instinct, of course, with your experience in solving problems, you can actually assume right away the correct direction. But if you are not yet used with that, then we need to, I suggest you will always assume a tension. Then if later on, by of course solving, and you will end up a negative, again, what does that mean? That is just the opposite. So if this, for example only, we will end up with an AB which is negative, it means it is the opposite direction, so that will become a compression. Okay, so again, going away is tension, going towards is compression. So let's start with joint A. So again, that is the application. So the reaction is going towards, since of course we can see it here, towards joint A, and then the member, if I will separate this joint, you will have a connected member AE and AB. So those are actually represented by forces, which I said I will assume this one initially as purely tensions. All of these are tension members. So AE going away, AB going away. So those are the unknown member forces that I will be solving within your joint A. So by using, of course, in your method of joints, what we need here are actually just summation of forces, okay, horizontal, vertical, since we are still on 2D trusses. But if we will proceed on 3D trusses or space trusses, then we will be including summation of forces to the z-axis. Okay, so summation of force horizontal, let's start with that. So assume always that going to the right is positive, so this is going to the right, positive 320, and then AB going to the right, so AB positive. So that is the only horizontal force. Simple algebra, transfer this one, this will become a negative AB. So what do we mean again by negative? It is the opposite direction. Since that is a negative, it will be the other way around. So initially my assumption is going away, so that is a tension, but it is given by the negative that should be going towards, which will be compression. So I can actually erase the negative, since again the negative only means the opposite direction. So therefore AB is a 320, but that is now a compression. But in case I will end up positive here, directly positive, then that will just be automatically my correct assumption, or my assumption is correct, I mean. Okay, so again, negative 320, so erase the negative, reverse that one, that will become a compression. Okay, so now summate vertical, we will be solving AE. So actually that is the only force, and there is none for us to equate that one. So AE is equal to 0. By the way, okay, going back here, whatever force experienced on the other end of the member is the same as the other end. If that is compression, compression. If that is tension, tension. Okay? So in here, if AB, okay, I will not be writing there F sub AB because that will be a lot for me to be writing. So I will just simplify it by AB. It means a force from A to B, or member AB at your joint A. BA is a force at AB at joint B. Okay, so that is the meaning. So again, as I've said, what is experienced on the other end will be the same on the other end. So AB is 320, therefore the same as BA 320, which are all compression. Summation of forces vertical. So okay, AE is equal to nothing for us to equate to 0. So that is now AE. So that will be the same as EA. So what do we mean by 0? So 0 force. So there is no force being exerted on that member. So that means we call that one the 0 force member, or that is not stressed, that is unstressed. So what does that mean? Even if we will try to remove that one, the the truss will stand. Okay, the truss will stand, since of course based on the solution that is 0, so it is not carrying any of the loadings. Okay, so AE is 0, this one is 0, this one BA is carrying 320 pips, which is compression, so it means this is being compressed. But later on we will talk about that if we will go on the summary of the answers. Okay, we are only done with joint A, so there are a lot of joints for us to discuss, so we would better continue. Okay, so let's proceed at joint E. So you can go directly at joint B, but if you will go here, okay, if you will try, let's say, go to joint B right away, we only have your AE and AB. There are 1, 2, 3, 4 members unknown connected to your joint B if you will go directly, since there are 5 total but only 1 is known. So even if we will apply summation of forces vertical, horizontal, we cannot solve, since these are only 2 equations. We can only solve 2 given, and these are, 2 unknown, and these are 4. So we cannot do that. So I'd rather move to joint E. So joint E, if I will now be considering this one, so isn't it the other connected member is already solved from the joint A, so which is AE, which is 0. So by the way I represent a 0 force member is without the direction or without the arrow itself. That is just a line, just to represent that there is a member within that direction, but there is no arrow. It means there is no stress or there is no force. Okay, so we have here the reaction, copy, away, and then that is away. And then this one I will always assume, okay, in the first place, if I do not know yet the member force, I will always assume to be tension, or which is going away. So we have here a connected EF, horizontal, so away, and then downward diagonal, which is EB, so away. So by the way, if you will try to notice, I always name the force starting from the letter of the joint I am considering. So that is A. So everything will be starting from A. AE, AB. That is E. So EF, EB, EA. So that is how I will name. That's why it is important for us to know that AB is equal to BA. Okay, or EA is equal to AE. Okay, so now this is the figure, but by the way, here this is important. Okay, that's why I tried to recall to you the what to call this one, the things that you discuss from your rigid bodies, wherein concurrent forces and so on and so forth are dealing with force systems. Since in your rigid bodies you discuss about resultant. If you have concurrent forces, you can convert that one, or if you say concurrent again acting on a single point, you can actually convert that one. Let's say there are more than two or more forces acting on a single point. You can combine that all of these and then consider that as a single force, which is a combination of all of these acting forces, and we call that one the resultant. Okay, and actually once we have the resultant, we can break that down into components. Okay, so for example is this one. Member EB, we cannot summate that one with vertical and horizontal, since that is not perfectly vertical or perfectly horizontal. That is inclined, so we need to break this down in what we call as the components. Again, recall from your statics of rigid bodies. So if I want to break this down, then there will be a component which is, since that is going away, isn't it? There will be a component which is going away, horizontal, which is going to the right, and then going away downward, since that is going down, which is tension also. So there are two components of this. If I will break this down so that I can include that one on the summation of forces horizontal and vertical. Okay, so that is what we will be doing with inclined forces. Break this down into horizontal and vertical components. That's why we need this slope. So by the way, you should know your slope triangle. Okay, where did I get this 3, 4, 5? I just reduce, of course, the dimension. According to this, that is 12. So it means this is 12, and that is 4 by 16. So it means each of these will be 16. So if this is 16 and that is 12, actually I can reduce that one. Okay, reduce that one. Since 12 and 16 are divisible by 4, so divide this one by 4, that will be 3. Divide this one by 4, that will be 3. But actually you can use directly your 12 and 16. Okay, you can use the triangle, original triangle. But let's say your number is thousands, that will be a lot for us to write, or that will be long for us to write. So I suggest you know how to simplify or to reduce your triangle. So if that is 3, 12 is reduced to 3, and then 16 is reduced to 4, then we need to find the hypotenuse. Okay, so this is the imaginary. This is just imaginary, that is not a part. Okay, that is just what we call as the slope triangle. Okay, so 3, 4, rise is 3, run is 4. So diagonal, compute Pythagorean. So 3 squared is 9, 4 squared is 16, 4 plus 9 is 25, square root is 5. Okay, so my slope is 3, 4, 5 triangle. So the same thing here actually, only that the direction of the line is different. But the rise is 12 and then run is 16, so 3, 4, 5. Okay, so this is the same as this is the same as that, since these are all the same dimensions. Okay. So now, if I will break this down, the component of EB going down is 3/5. Okay, you should recall your trigo or basic trigo. Or if you want, you can solve the angle, but that will be a little bit longer for the solution if you are using an angle, because you will be using sine, cosine, okay, and so on and so forth. So I'd rather suggest the slope triangle. So all you need to do is incorporate the fraction. So for a vertical, that is 3/5 of the EB. Component horizontal is 4/5 of EB. So that will be going there. So now let's try to take summation of forces vertical. So going up, so what are the going up? Is 105 positive, since going up is positive. EA is supposed to be, however, that there is no force, so that is 0. So we do not need to include that one. What else? There are no more vertical, but as I've said, there is the component of this, which is going down. Okay, component is going down, component is going to the right. Okay, you should know how to break this down from your rigid bodies. Okay, so going down, therefore that is a negative. And what is the fraction of EB going down? 3/5. So minus 3/5 of EB. Now, calculating this one, this will go positive, divide both sides by 3/5. You will have your EB, force EB to be 175. Positive, so it means our assumed direction of EB is correct, which is 175. Tension, keeps tension, okay? So EB is the same as BE, okay? So that is our member force here, okay? So that means that is under tension. So let's proceed with summation of forces horizontal, okay? So summation of forces horizontal, okay? So this is the force, that is the force, and the component of your EB. So all going to the right are positive, so EF is positive. What else? EB, the component of this is positive, and what is the component of that? 4/5 of EB. So 4/5 of EB. And then this is going to the left, which is a negative 320. So by the way, we already have your EB, which is 175, substitute that one. And then of course, simple algebra combined, transfer on the other side will give us positive 180. So positive again, that means our assumption, which is tension, is correct. So EF is equal to FE, which is equal to 180 keeps in tension. Okay. So don't worry, there will be a lot of member forces. So later on we will, it's better for us to outline this one. You can use table, or we can actually plot that one within the entire figure. Now let's proceed with the next joint. Okay, I already completed joint A, joint E. So I already calculated all of this 1, 2, 3, 4 members. So if I will move here, again, the same thing. I only knew these 2. There are 3. So I cannot yet proceed to B unless I will first pass with F, so that I will be solving this member. So I will start with F. Okay, at joint F. So FE is tension. Actually, now we already know the actual scenario of FE. And going back there, FE is tension. So we should assume that one to be the correct direction, FE, which is tension. And then this one, I do not know that yet. Okay, that is what I will be solving here at joint F. So I will assume tension. And so with this, FB, tension, since I do not know yet the direction. Okay, and then now I will summate forces. Okay, now look at this. At joint F, there is now the load, 30 kips. We need to include that one, just like including your reaction. Include all the forces acting on the joint. Okay, so together with the load, 30 kips going down. Okay, summate forces horizontal, going to the right positive. So this is positive, that is negative. So negative FE. And then all we need to do is transpose. This will go positive on the other side, isn't it? And then that is go positive. FG is equal to FE. So FE, we solved that one previously to be 180. Okay, to be 180. So if that is 180, tension, that is the same as the FG. FE is 180 tension, that is the same as FG. So FG is equal to the other side. Okay, what is experienced on the other side is the same on the other side. So FG is equal to GF, which is 180 keeps tension. Then summation vertical, going up is positive. So this is now all going down, so negative. FB, negative 30. Transpose, this will become, this FB will go on the other side to be positive. So FB is equal to negative 30. So again, the negative only means the opposite. So my assumption here is wrong. So that should be going towards. It means it is a compression. So FB is equal to BF, that is 30 keeps compression. Okay, now let's proceed with the next joint. I already completed. Okay, 1, 2, 3, 4, 5, 6. So actually I cannot proceed with joint B. Since I already know 1, 2, 3, I can solve the remaining 2. So if I will go there at joint B, okay, let's try to apply. We already know the directions, the actual directions of this, so that is what we will be following. So your BA, we solved that one a while ago to be compression, so that will be going towards, okay, the point. BE, we solved that one previously also. BE is the same as EB, which is tension, so that is going away. Okay, this one away. And then BF, we solved that one here to be compression, so going towards. So the only unknown is BJ and BG and BC. So the same thing, summation forces horizontal and vertical. So let's start. Okay, if you will try to summate horizontal here, there are 2 unknowns, BC and the component of your BG. Again, we will break this down, this inclined into horizontal and vertical component. Okay, so these are given, or already solved. These are the unknowns. So if I will break this down, there's a horizontal and vertical. So if I will start with summation of horizontal, I will end up with 2 unknowns, so I cannot do that one. I'd rather start with summation of vertical. So if I will summate vertical, what are the vertical forces? Your BF, the component of this, which is already solved, and the component of that, which is to be solved. Okay, so let's do that. The 3/5 of BE is going up, so positive, and 3/5 of BG, which is the unknown, going up, so positive, and going down BF, so that is a negative. So substitute whatever we know. Okay, so BE, 3/5 of BE, your BE is solved before to be 175, and then your BF is already solved here to be 30. Okay, don't worry about now the tension and compression, since already that is applied on the direction. So all we need to do is solve your unknown BG. So combine simple algebra, you will end up with BG to be negative 125. So again, negative only means the opposite. I assume that to be tension, but in the case which is a negative, it means that is the opposite, which is compression. Okay, so BG is equal to GB, 125 compression. Now I will move to summation horizontal. So going to the right, positive, so this is going to the right, so BA is positive, BC, the unknown, is positive, and then the component of this is going to the left, so negative. But first I will start with this going to the right, component of this. But by the way, isn't it, this is compression? It's up to you. Since that is compression, you can reverse that one before establishing your summation of forces horizontal. But for me, since I already drawn that one this way, I will follow whatever I assumed here, but I will carry the sign, which is meaning that is the opposite. I will carry the negative, it means that is the opposite. But again, when you solve this one and you prove that one to be compression and you reverse this one, no need for you to include the negative in the next solution. Okay? But since, again, as I've said, I will be using the original assumption, which is tension, and that is supposedly compression, therefore, in here, I will be substituting that BG to be as a negative. Okay? So that is just simple analysis. Okay? So again, what else? Let's start again. Summation horizontal is BA going to the right, BC going to the right. I will follow this, which is tension still, okay, going to the right. So a component of that is going to the right, 4/5 of BG, and then negative 4/5 of your BE, which is going to the left. Substitute is given, whatever is given. BA is 320, okay, 320, and then BC, that is the unknown, BG, that is already solved here, but as I've said, in my equation here, I consider that to be tension, but the answer here is compression, therefore I will include the negative. Okay, but if I consider that to be compression already, then no need for me to carry the negative. Okay, so now BE is 175. Okay, again, those are just coming from these values here, 320 and 175. 320 and 175. So simple algebra, calculate, transpose. BC is a negative 80. So again, negative means the opposite. So my assumption of tension in your BC will be the opposite, which will be compression. So BC is equal to CB. 80 keeps compression. So now let's move to joint C. Okay, so we completed A, B, E, and F. So again, if you'll try to look here, if I will go directly to G, okay, we know this one, we know this one, we know this. But in your joint G, there will be 3 unknowns, so we cannot yet solve that one since we only have 2 equations, summation horizontal and summation vertical. So I'd rather start with joint C. If I will do that, okay, CB, we solve that one. CB is the same as BC, which is compression, so that will be going towards joint C. CG, that is unknown yet, so we will assume that one outwards. CD, assume that one outwards. Okay, summation horizontal, CB is going to the right, CD is to the right, substitute what is given. So CD, CB is 80, CD is what we will be solving, this will go negative on the other side. So CD is compression, the opposite, since that's a negative. So CD is equal to DC 80, which is compression. So your CD is compression. And in summation vertical, there is nothing for us to equate with your CG, so that is 0. So CG and GC is 0. So another 0 member force. Okay, 0 member force or 0 force member. So this is 0. So it means it is not carrying any. And so with this. Actually, you can, by merely looking at the figure, you can predict if that is a 0 member. 0 force member. Since here, by merely evaluating your joint C, summating vertical, there is nothing for us to equate with your vertical here. So automatically this is 0. And so with this, summating at this joint, there is nothing for us to equate with this vertical, so 0. Okay, so these are now your forces at joint C. We already know this one, and this. So we already know 3 members at your joint G. So we can now proceed with your joint G. So joint G, you know GF, you know GB, you know GC. We will be solving here GD and GH. GC is 0, so there is no arrow. And GF, we solved that one previously. GF is 180, which is tension, so that is going away. And then GB, which is, we solved that one, GB is compression, so it means that is going towards. Your GC again, 0 member, so no direction. I will assume this yet to be tension since I do not know yet the actual. Okay, so that will be my assumption to solve this too. So let's start with summation vertical. So summation vertical, if I will submit vertical, so what are the vertical forces? 30. This is, no need to include this one since that is 0. The component of this one and the component of your GD, which is the unknown. So every going up is positive. So component of this 3/5 of GB is going up, so positive, negative. Negative of this 3/5 of GD, which is the unknown, negative, going down, and then negative 30 going down. So substitute what we know, which is GB 125. Then simple algebra, GD, solve GD will be 75. It means our assumption, since that is positive, our assumption is correct, therefore that is tension. So GD, DG is equal to 75, which is tension. Summate horizontal, okay, going to the right, positive. So horizontal, so what are the horizontal? This one, this, and the components of these two inclined forces. So all going to the right is positive. So going to the right, GH, so positive. Let's start with GF. To the left, so negative. To the right, GH, positive. And then to the right, component of this one, GB, which is 4/5. To the right, snip, so positive. To the right with your GD is still, so positive, 4/5 of GD. So substitute what we know, okay? So GF, we solved that one before that, that is 180, so negative 180 since that is a negative. GH, that is what we will be solving. GB, that is already solved previously to be 125, okay, this one. And then GD, that is solved here, which is 75. And now solve your GH, which is exactly positive 20, so it means our assumption is, which is tension, is correct. So tension, GH is equal to HG, 20 keeps tension. Okay, so we are now good with joints A, E, B, F, C, G. We can now finish it within these 3 joints. So let's proceed. Okay, let's start now with joint H. So again, analyze. We already have all of this, starting from these members going to the left. Okay, so if I will consider your joint D, I cannot solve. Actually, I can solve. Okay, I can solve since there are only 2. But I'd rather start with joint H, since that is simpler. Okay, so if I will start with joint H, so going down, that is the load, I need to include that one, and then HD, I do not know yet. Okay, I will assume tension, and then I will assume tension to HI since I do not know yet, but GH or HG, I solve that one to be tension, so that is going away. Okay, so summation horizontal, HI is equal to HG, or positive, negative, so it will go positive. So they are equal, so whatever HG is, which is positive 20, that is the same as HI. So tension, since HG is tension. So tension. Summation vertical, okay, all are going down, so negative, negative, so HD will go positive, so HD is negative 30. So it means my assumption initially, tension will become compression. So HD, I'm sorry, here pala. Okay, so HD, which is now assumed to be tension, will now be compression. So HD DH is equal to 30 compression. Okay, so proceed now with your point D. So we already know 1, 2, 3. We will be solving your DI. So we solved this one previously, that is compression. So going towards joint D. Tension, we solved that one, which is going away. Tension. Okay, we solved that one here to be compression. So going towards. So this is now the only unknown here. So actually, since we only have one unknown here, and that is inclined, I can break this down into horizontal, vertical. So if I will submit horizontal, I can solve that one. If I will submit vertical, I can solve that one, since it is only one unknown within your one joint. So actually, I can finish that one by maybe using vertical or horizontal, but I'd rather show you the both, okay? So this is one way of checking. If you will use these two solutions and you will end up with the same value of di, then you are pretty sure, okay? You are having additional confidence that your answer is correct, that your answers previously are correct, because whatever we are solving right now is being affected by our previous answer. So it means if we try to prove right now and that is not being proved, that means we made mistake with the previous solutions. Okay, so let's start. Let's say I will use summation of forces vertical. So all going up is positive, so this is going up. 3/5 of that of dg is positive, and 3/5 of di is going up, so positive, and then dh is downward, so negative. We solve dg to be 75 and then dh to be 30, so the di is the unknown. Solve that one, negative 25. It means negative, my initial assumed, which is tension, will become compression. So that is our solution. We already completed, actually. We already completed this one and this. So we already know all of the members. But, okay, since there are still one more equations that I did not use here, I can use that one as checking. And if you will try to look at this, I did not yet move to joint I, and I already know all of that forces, isn't it? So again, the final point, make use of that one as your joint of checking. Or if we say joint of checking, that is the joint for you will be checking. If you will satisfy all the equations at that joint, it means that you are 100% sure your solution within the previous members are correct. Okay. However, let's first solve the pair equation of that. So instead, let's say I will consider horizontal. I should end up with the same as this. Okay. So summation horizontal, all the horizontal. So this is going to the right, so positive. Component of di is to the right, so 4/5 of di is positive, and then this is to the left, so 4/5 of dg is negative. So substitute dg 75, substitute dc 80. di will be solved the same as negative 25, so it means a negative is compression 25 kips. So by simply comparing this, it means my confidence within the previous answer is a little bit sure. However, I'm not pretty sure, since I need yet to finish the joint. So again, as I've said, we are already finished solving all the member force. So actually, supposedly, I am not required to pass to your joint I, but I'd rather use the final joint as my way of checking. Okay, so I suggest that one always. Okay, so if we will now proceed, let's check that one, or checking at joint I. So let's try to apply the checking at joint I. Again, I already know all of the members, so let's separate joint I. So hi, we solve that one to be tension, so away, and then di compression, so away and then towards. Okay, and we have there to carry the 15 kips. So summation horizontal, so hi, and then the component of your id, or ih in the component of your id. So component of id is 4/5, which is positive since that will be going to the right, and ih is negative. So substitute 25, id is 25, ih is 20. This will become 4/5 of 25 is 20, minus 20 is 0. So by merely satisfying the equation, okay, the other side is equal to the other side, so 0 is equal to 0. Yes, that is true. Therefore, okay, we satisfy this one. Finally, let's try to satisfy vertical. Summation vertical, so the component of this is going up, isn't it? So 3/5 of id is positive, and 15 is going down, so 15. Substitute id to be 25, that is multiplied by 3/5. 3/5 of 25 is 15. So 15 minus 15 is, I'm pretty sure, 0. So 0 is equal to 0. So we finally prove that we are 100% sure of our answers. Since we satisfied the final joint, all of the equations in your final joints are satisfied, so we are 100% sure that our solution is correct, or our answers are correct. So actually, this is now the outline. So this is how you will outline your answers. Okay, since we are analyzing members, especially if that is more than 10 and so on and so forth, it is better for us to present this one in tabulation, or you can include that one on the figure. So I prefer here to include in the figure, since I want to explain the reason, okay, of compression tension within the applied type of loading. Okay, so let's try to include that one, or to outline that one using the figure. So if we will try to substitute, okay, so again, all of these forces here are the ones we solved a while ago. And we solved that there are two zero force member, your AE and CG, okay. It means these members are not carrying any forces. So let's try to use color coding, okay, so that I will not be including there the compression tension, since that will be a lot for me to be including in the figure. It will just be making our figure complicated. So let's try to apply color coding. So green is for tension, and then red is for compression. So actually all I need to do is what I did here is that I just copy this one to the figure. So all of these numberings here, all of these forces here are the ones we solved. And again, all the tension, I color that one to be green, and then all the compression, I color that one to be this pink, if that is how you look at this, pink, okay. And I colored your zero force member as blue, so that means it is neutral with the color of the member. So it means it is not stressed, it is not stressed. So look at this. Is that reasonable? You can now actually check, okay, based on the loading. You can now try to visualize if that is possible, okay, if the forces are possible. Since if you will try to look at this is ruler that is free to move upwards. This is pin, so that is restricted from moving upwards and horizontal, or vertical and horizontal. Okay? So if I will be loading this, okay, imagine this as a single member. If I will be applying these loadings, what will happen? This part here on top will be stretched, isn't it? And the part below will be compressed. So, actually, I can explain, I can visualize now why. Some of these are tension, some of these are compression. So again, look at this. This is being restricted here, and that is supported there. So if I will load this one, it will not rotate. Rather, the entire system of the truss will be stressed in different manners. So again, since all of the forces are going down, so it means this will try to bend the truss that way. It will bend downward. So it means the upper part will be stressed, tension, or be under tensile stress, and then the below will be under compression. Just imagine, okay, just like your mechanics, okay, if this is, for example, again, if this is the truss, let's say that is solid, but of course let's imagine that is the truss. If you will be loading these ones by forces going down, that will bend your truss that way. So you will expect whatever is below will be compressed, and whatever is on top will be stretched or tensile. So actually that's it. That is the importance of outlining, or yes, indicating the forces within your figure, and then try to visualize if that is possible based on the loading and of course on the type of supports. Okay, so that is for the method of joints. So actually, again, the general procedures that you have now the loading. By the way, do not worry here about the indeterminate, since of course we will try to focus ourselves on determinate structures. Later on, once you will go with your theory 2, that's the time you will worry about indeterminate. So it means that whatever I gave you right now is solvable by simply summation of forces, horizontal, vertical, and summation of moment. Okay. So the general procedure here in analysis of truss using method of joints is for you to solve first the reaction. Now once you have the reaction, start from point to point. Okay, you can actually jump. Okay, just like this. Let's say I did not yet solve any of that. I can actually jump directly to joint C. Why? Since if I will sum it vertical, I can solve that this is 0. If I will sum it horizontal, we cannot yet use this one, since what we can solve is only this. But we can jump directly here on the other end. Since if I will try to cut this, separate this joint, summate vertical, I can solve this incline, and then summate horizontal, I can solve the horizontal member. So actually, I'm not saying that always start with the reaction. No, you can start anywhere as long as, of course, you can solve the member forces and then proceed. Okay, so that is the challenge, of course, of method of joints. You need to visualize if you can solve the forces within the joints. Okay, and of course, the challenge here is that you will be passing in all of the joints. So imagine how many joints. For example, that is a complicated truss, and you have a lot of points, a lot of joints. Then you will be having a long solution. Then I will be now, don't worry, we will be having now the second method on the next unit. And actually, later on, if we discuss these joints and the second method, we can actually combine this, okay, for simpler or easier solution. But for now, let's stick with method of joints, since of course that is the coverage of this unit discussion. Okay, so that's it. The general procedure is that you have the loading, solve the reaction. Once you have this reaction and loading, distribute that one within the members. And that is what we call the member forces or member stresses if you will be solving the stress. So method of joints, all you need to do is isolate the joint. What will this one? Consider all the members connected and represent that one by forces. If tension, the arrow is going away. If compression, the arrow is going towards the joint. And then summate horizontal, vertical, you will solve whatever is unknown that is connected at that joint. Okay, so that is the flow of the analysis of a truss using method of joints. So again, I will only be giving you one example, since you will be repeating this again and again. Since of course, if I will be giving you a lot of examples, I can see that most of the students right now are actually just comparing examples with problems. So if the problem is different from the example, they're having a hard time since they are used in doing that. So what I am doing right now is just to give you one example, but I discuss all the concepts. If you say concepts, those are the things to do, even if you will solve a different problem. Okay, so again, so how I teach the subject is by concept. I will not be teaching this by the numbers of examples, okay? Because as I've said, again, some of the students are just comparing. If these are different, then they will now be having a hard time analyzing. So I'd rather explain the concept. You will take it as a concept and then apply in any type of problems or any type of situations. Okay, so let's review some of the important concepts discussed in this unit. Okay, so first is, in analyzing trusses using method of joints, equilibrium should be satisfied in all joints. Okay, so that is the main concept of analysis of trusses using method of joints. All we need to do is satisfy the equilibrium within the joints, since of course in the first place the entire structure should be equilibrium. So that should be true to all of its joints also. Okay, so if we will try to satisfy the equilibrium within the joints, that is how we will be solving the member forces, given the other member forces already, okay, which is solved on the previous other joints. So that is the main concept of the method of joints. Satisfy the equilibrium in all of the joints of the trusses. Second is that the final joint is utilized as checking of the previous solution. So again, this is actually not required if you are solving. Okay, but for what to call this one? For what to call this one? For the for more reliable result or for more reliable answer, we need to check. So that is the advantage of using the final point. Okay, since of course, if you will solve from joint to joint, you will be solving all the member forces, but there will be one joint that will not be used, and you already solve all of the member forces. So I suggest always use this one as your way of checking for the others. So how do we know that that is correct using that final joint? Is you need to satisfy all the equilibrium scenario within the final joint. So that is the summation of forces horizontal, summation of forces vertical. So simple as that for the analysis of truss using the method of joints. The only challenge here in this method is that if there will be a lot of joints, then there will be a lot of solutions. Okay, but that is simple. Only summation horizontal, summation vertical. Okay, so that is for this unit. Okay, so if you have any question, you can comment that below the discussion, or we will be discussing that one on the next live meeting. Okay, so thank you very much for watching.